Sorry, so just to say that the next talk is going to be given by Peter Brown, and it's going to be on device-independent lower bounds on the conditional for Neumann entropy. So please, you can start whenever you want.
Thank you. Yeah, so in this talk, I'm going to speak a little bit about some recent joint work with Hamza and Omar on computing lower bounds on the rates of device-independent protocols. So we just saw a talk by Mate about upper bounds on the IQKD protocols, and here we'll kind of have the converse where we look at lower bounds on the rates of protocols. And the paper is available in archive, and I think if you're interested in the results, I recommend you go have a look at the paper for more details. Okay, so we've just seen this sort of picture where we have two devices, or we could also have more devices that we treat as black boxes. So we allow ourselves to interact with our devices by feeding them classical inputs and receiving classical outputs from them. And we assume during these interactions that the devices cannot communicate to one another. And then we know that if these devices are violating a Bell inequality or producing non-local correlations, that they must also be producing some randomness in the outputs. And this leads us to build on top of these tests for non-locality, so-called protocols for device-independent cryptography. For example, we can use these non-locality tests to generate randomness, and at least for some non-locality, as we've just seen in the previous talk, we can also use these tests for generating a secret key between these devices. However, in order to actually understand the performance of these protocols, and actually also in order to prove the security of these protocols, we need to understand better a quantitative relationship between the non-locality and the amount of randomness that's being produced by these devices. And this is what we know, what we refer to as the rate of the protocol, that is the amount of randomness that we're producing per interaction with our devices, if the devices violate some Bell inequality, for example. And this is the main task of this work, is developing some numerical method to compute lower bounds on this rate, which is sufficient for proving security. So from the cryptographic perspective, we might think about the scenario a bit more like this, where we now have our devices in some secure laboratory, but we also have an adversary here. And for example, we allow our adversary to share entanglement with the initial quantum state that's shared between the devices and is used to violate the Bell inequality. And we also allow our adversary, for example, to choose the measurements inside the devices, and she can really prepare this system as she wishes. Okay, but so if we're interested in the randomness being produced by devices, what measure of randomness are we going to use? And it turns out the correct measure of randomness is the conditional von Neumann entropy. So for example, if we're just interested in randomness generation, then we can look at the conditional von Neumann entropy of the outputs of both the devices. Or if we're interested in generating a shared secret key, we can look at the Devatak-Winter bounds. As you can write it as the conditional von Neumann entropy of Alice's output given Eve's information minus the conditional von Neumann entropy of Alice's output given Bob's information. And in order to understand the rates of our device-independent protocols, we want to be able to compute device-independent lower bounds on these quantities. Okay, so I'd like to say a little bit more about exactly what I mean by a device-independent lower bound. So first off, you fix some set of constraints on the probability distribution of your devices. So for example, this is really something that you might check during the protocol. For example, this could be a Bell inequality violation. So you're going to assume that your devices violate some Bell inequality, or they're producing some non-local statistics. For example, we could set the constraints to be that the devices are going to win the CHSH game with probability at least 0.8. This could be a valid constraint that we can add to this set. And then we say a strategy for our set of constraints is just really any devices that the adversary can prepare that would satisfy the constraints that we impose on our devices. So more formally, the adversary can choose some joint Hilbert spaces of Alice, Bob, and Eve's devices, a state on that joint Hilbert space, measurements for Alice's device, measurements for Bob's device, such that the distribution induced by that system satisfies the constraints that we've imposed on our devices. Okay, now for each strategy that the adversary can come up with, for each devices she can prepare, we can associate a post-measurement state to a given strategy, and that allows us to associate a conditional von Neumann entropy to each strategy. Okay, and then a device-independent lower bound is just for our fixed set of constraints on the devices, we want to compute the infimum over the conditional von Neumann entropies of all strategies that satisfy our constraints. And this is really the problem we want to solve in the end. Unfortunately, this is a very difficult problem to solve. First off, it's a non-convex optimization problem. And also because we're working device independently, we, for example, have no bound on the dimension of the systems involved here. So the adversary can pick infinite dimensional systems. So if we try and do some sort of naive optimization, we'll quickly run into problems. But it's sufficient, as I mentioned before, for security purposes to get lower bounds on this. And this is kind of what we're going to aim to do, is try and get the best lower bounds on this quantity that we can. So there have been kind of numerous works trying to actually derive lower bounds and tight lower bounds on this quantity. And there's been a series of works that have done this actually analytically. So it turns out for if you have sort of a Bell inequality as your constraint, and your devices have 2 inputs and 2 outputs, that often you can actually reduce the problem to 2-qubit systems and actually solve this optimization problem explicitly. Okay, and several works have done this, and this leads to tight bounds on the rates of your device-independent protocols. They can solve this optimization problem exactly. But it is restricted in its scope of applicability because it does only apply when the devices have 2 inputs and 2 outputs. And typically the constraints that you have in your that you impose on your device have to be sort of sufficiently nice. Or at least so far, people have only solved this for like quite nice constraint sets. So you might look for maybe a numerical approach so that can handle sort of general constraint sets and more general devices with more outputs and more inputs. And one such approach would be to use the Min entropy. Okay, so the Min entropy is a lower bound on the conditional von Neumann entropy. So if you replace the conditional von Neumann entropy with the Min entropy in your rate optimization, you can get a lower bound on the rates, which is sufficient. And the nice thing about the Min entropy, though, is that if you write the resulting rate optimization, you can actually relax it to what is known as a non-commutative polynomial optimization problem. So kind of roughly, this is just an optimization problem where we have something of the form where we have a trace of our state multiplied by some polynomial of some operators. And we allow ourselves also to have maybe polynomial constraints on those operators as well. And the really nice thing about non-commutative polynomial optimization problems is actually we have a kind of a very nice technique known as the NPA hierarchy, which allows us to relax these problems to semi-definite programming problems. And this means that we can compute lower bounds, at least on the Min entropy, which in turn are lower bounds on the conditional von Neumann entropy, using semi-definite programming. And in particular for the Min entropy, it's very easy to compute these bounds. The unfortunate thing about the Min entropy is that it can be a lot smaller than the von Neumann entropy. So this tends to lead to quite poor bounds on the rates of your protocols. So more recently, there have been some works that have tried to extend the Min entropy approach and try and derive better non-commutative polynomial optimization problems that are lower bounds on the von Neumann entropy. And these works ended up with rates that were in general a lot better than the Min entropy, but there was still certainly some room for improvement. In particular, it was not clear that either of them could produce tight bounds, and it seemed that neither of these approaches were better than the other, kind of indicating that there was some sort of better approach. And in this work, we're going to try and really extend this approach further and try and get something that we can show is able to recover these tight bounds and improves a lot even on these more recent numerical techniques. So again, we're going to try and look for kind of this approach, this general numerical approach of deriving these polynomial optimization problems. In particular, what we define is a sequence of quantities, we call them HM here, that look like this, such that each of these quantities is a lower bound on the conditional von Neumann entropy. But what we also look for is that these quantities actually converge the conditional von Neumann entropy as m tends to infinity. So this can allow us to at least hope, at least theoretically, that our approach should converge to the optimal values. And what we find actually when we apply this in practice is that really we do end up in a lot of cases very close to the optimal bounds. The optimization problems that we actually solve in examples end up being, at least in the way that we implement them, more efficient even than the more recent numerical techniques. And our approach actually has a slightly wider scope than these techniques as well, in the sense that we also prove that our method produces lower bounds of the Ritz even when the systems are infinite dimensional. Okay. So in the work, we actually prove something slightly more general, and we work with the relative entropy. So this is an expression for the relative entropy, and you can use it to define your conditional for Neumann entropy using the following formula. Okay, and then the goal of the work was to derive something of the following form, which was we want to derive upper bounds on the relative entropy in terms of some optimization, some polynomial optimization, where we have something like trace of rho times a polynomial of some operators plus trace of sigma times potentially some different polynomial of some operators. And we also wanted to show that this right-hand side converges to the relative entropy as m tends to infinity. Why might you expect that even something like this exists? Well, we know that at least the relative entropy is jointly convex. So we know that we could at least write it with some variational form that is linear in rho and sigma. And then the question is, maybe this variational form can be expressed in terms of polynomial constraints, or maybe we can relax it and to maybe a slightly weaker set that it can be expressed in terms of polynomial constraints. So this is maybe some motivation as to why you might expect such a form to exist. But the important thing is, why are we looking for something like this? But well, it turns out that something like this is basically sufficient for later optimizing using the NPA hierarchy. So if you have an upper bound on the relative entropy like this, and the important thing really is that the right-hand side is linear in rho and sigma, and it doesn't have any sort of explicit dependence on the dimension of the systems. Okay, and if we have something like this, and we could also have polynomial constraints, as I mentioned before, then we can later convert this into a lower bound on the conditional von Neumann entropy, and then actually use the NPA hierarchy to do some actual computations on this. Okay, so I'd like to kind of give an overview of actually how you derive such a thing, but just at a very high level, and I refer you to the paper for more details. But basically, we want to define a sequence of upper bounds, and where this sequence comes from is actually a sequence of approximations of the logarithm function. So actually, if you write the logarithm as an integral, you can write log of x as the integral of this integrand over t from 0 to 1. And using a technique known as Gaussian Quadrature, you can approximate an integral by a weighted sum of the integrand evaluated at different points. So if we write f of t of x as this integrand, we can approximate this integral here, which is the logarithm, by some sum of some weights times fti of x. And this value m here is just just some natural number, and you can choose it. As you increase m, the idea is that these approximations of the logarithm get more and more accurate. And you can do this in a very particular way known as Gauss-Radau quadrature, such that the approximation of the logarithm is actually always a lower bound on the logarithm. And this is important because you want to bound the relative entropy in a certain direction. Okay, and then the idea is that we apply this approximation to the logarithm to the relative entropy in a particular way. And what we end up with kind of at a high level is an upper bound on the relative entropy in terms of some weighted sum of some quantities, which we call DFTI, which kind of roughly what's known as quasi-relative entropies, which are, in some sense, relative entropies where you replace the logarithm with a different function. And in this case, we replace it with these FTIs. Okay, and then the next step of the proof is to show that each of these DFTs can be written as an optimization problem of the following form. In particular, we have the structure that we want, trace of rho times a polynomial plus trace of sigma times a polynomial. And then if you put these last two steps together, you end up with kind of what we were looking for. So an upper bound on the relative entropy in terms of some optimization problem. And with some more work, you can actually show that this right-hand side converges as m tends to infinity. So as you kind of approximate the logarithm better and better, this thing should converge. Okay, and so yeah, as I mentioned before, we can apply this. We can define our conditional von Neumann entropy in terms of the relative entropy. And when we apply the upper bounds on the relative entropy, we'll get lower bounds on the conditional von Neumann entropy. So you can do this. And then if you replace the conditional von Neumann entropy in the rate calculations, this infimum over all strategies, with these lower bounds, then you'll end up with a lower bound on the rate in terms of something that looks like this. And it's not particularly important exactly the expression itself. But really, the important thing, as I mentioned before, is that we have this objective function that's linear in rho. And yeah, we have here, we're able to express it in terms of the operators that are kind of meaningful in the device-independent setting. For example, Alice's measurement operators, because we're interested in the entropy of Alice's outcomes. These appear here, and then we have these Z operators that act on the adversary system. And we have this infimum over strategies here, but as I mentioned before, these strategies include the state, the measurements of Alice, the measurements of Bob, but now they also will include these Z operators that act on the adversary system. Okay, and the idea now is that this form is sufficient for us to actually relax this to a non-commutative polynomial optimization problem. So in particular, we just drop this tensor product structure here, and then we impose that operators that acted on different subsystems, for example, this M and this Z, should now commute. And this gives us a slightly weaker problem, so we'll get a lower bound on this infimum. And the important thing is that this will now be a non-commutative polynomial optimization problem. And we know as before, we can relax that problem further and get a further lower bound by using this NPA hierarchy. And this just gives us then a sequence of STPs to solve that each of them should be a lower bound on the rates of our protocols. Okay, on a technical level, we can also show that the NPA hierarchy will converge for this problem because we can actually impose explicit bounds on the operator norms of these Z variables here. Sort of importantly for applications as well, we can actually, I've expressed this for a particular conditional von Neumann entropy here, so just Alice's output given Eve's information, but you can actually derive, because the relative entropy can express different conditional von Neumann entropies, you can actually derive similar results, for example, for the entropy of both the outputs, or if you want to average over the inputs of Alice as well, or you can do other expressions as well. For example, this method works for multipartite scenarios beyond 2 parties. Okay, so I'd like to present some of the kind of the results that we got from actually computing these things. And so we applied our method for example, randomness generation and looking at rates for key distributions as well. We looked at different constraint sets. For example, we constrained our devices by some winning probability in the CHSH game. We also looked at constraining our devices by the full some pre-chosen full distribution. So for example, you can think about this as sort of the strongest constraint that you can have in a device-independent setting is to know exactly the full conditional distribution. So the idea is that this constrains the devices more, and we can hope that this gives us the best rates possible from our devices. Okay, and we want to make this maybe a bit interesting, kind of or relevant for experiments. So we looked at devices with some fixed detection efficiency. So this is just some each device with some probability eta, it will succeed. And with probability 1 minus eta, the device will fail. And when the device fails, we just record that as some particular outcome that we're allowed to choose. And this allows us to avoid the so-called detection loophole. Okay, so the first plot I'd like to show is shows that our method can at least in certain settings recover tight bounds on the rates. So for example, if we constrain our devices by winning probability in the CHSH game, and we look at the entropy of Alice's output given ease information, we actually know a tight lower bound on this quantity. So this was given in one of those references I mentioned earlier, and it's plotted with this red dotted curve. And what we find is that as we increase the value of m, we end up getting better and better lower bounds on this quantity. And by the time that we reach the 8th optimization problem in our sequence, we actually agree with this tight lower bound up to several decimal places. So this demonstrates that we can at least recover tight bounds in certain settings. And yeah, so in this plot, we looked at devices with some fixed detection efficiency, and we wanted to look at the randomness generated by both the outputs. And we constrained our devices by some chosen distribution. So at each detection efficiency, we allow ourselves to pick a distribution from the set of 2-qubit distributions that maximizes the rates. And we compared our method with the 2 recent numerical methods. And what we see in this plot is that everywhere, for example, our method, previously the 2 recent numerical methods, neither of them did better than the other, but we see that kind of our new method does everywhere a lot better than these 2 recent numerical methods. So it's very nice. And we also looked at QKD rates. So we're looking at bounding the Devatek winter bound. And in this plot, again, we constrain the devices by some full distribution. And for our technique, we're looking at devices with some fixed detection efficiency and how much key they can generate. And for our devices, for our technique, we constrain our devices by some full distribution, and we compare it with sort of the best known protocol previously, which was based on the tight analytical bound for the CHSH game. So this is this red curve here. And what we see is that everywhere our technique improves upon this CHSH protocol. And kind of the interesting thing is where these curves kind of drop to 0, because this tells us sort of the threshold for the noise that we can tolerate in our protocol. So this says, what's the minimal detection efficiency we need in order to generate a secret key. Okay, and what we see is that for this CHSH-based protocol, it's actually, we can't see this exactly on this plot, but this will drop to 0 around 82.5%. And what we see is that with our technique, we're able to kind of push the noise thresholds back to around 80% or even further below if we were to try to go further. And this is kind of interesting because this tells us that the sort of noise thresholds for at least photonics-based experiments are around this 80 to 82% mark, and we can really kind of this kind of puts the this kind of says that it's likely that we could actually have a kind of a photonics-based DIQKD experiment in the near future. So using our technique. Okay, so to wrap up, I've introduced a new general method to compute the rates of device-dependent protocols. We can prove that certain aspects of this converge. For example, the upper bounds and the relative entropy we can show converge, and we can show the NPA hierarchy converges, but a full convergence statement we don't quite have. But we do actually observe in practice that our method can converge to the tight bounds on the rates. We saw that when we compared it with the other numerical techniques, we found that it improved over those, and you can also one can also show that it actually, one can also implement it in a way that ends up being faster than these previous methods as well. And sort of importantly, it also applies when the systems are infinite dimensional. And one thing that I think is important to mention is that it can be used directly with security proof techniques, for example, the entropy accumulation theorem, in order to prove the security of these protocols as well. Maybe some questions for the future. It would be nice to better understand kind of the convergence of the technique in the fully. For example, we have an issue where we dropped from this tensor product structure to the commuting operator structure. There can be a gap there. Okay, this question was kind of answered yesterday, maybe. In particular, there was a paper on the archive yesterday that showed that you could actually do DIQKD with, I think, cold atom systems. But I think the method that I presented here shows that it may be also possible to do an experiment with photonics-based systems. In order to do this, we'd like to we're looking into kind of modeling our experiments a little bit better and doing also a finite size analysis with this numerical technique. And also theoretically what we proved from the theory side of things is that upper bounds in the relative entropy, and the relative entropy can be used to define other entropic quantities. So whether this technique also has applications beyond kind of the standard device-dependent protocols of randomness generation, conference key agreement, or key distribution, is maybe some interesting work for the future as well. So with that, I'd like to thank you, and I'll leave you with some references.
Great. So thank you very much for the very clear talk. Now there's time for a few questions. So if you have any of them, please write them in the chat or on Slack. And in the meantime, I have a question of my own, a bit related to the last thing that you were mentioning. So
Yes.
just concerning the method itself, have you tried to derive it for some other quantities, like, I don't know, for example, instead of the usual relative entropy and the conditional for Neumann entropy derived from the usual relative entropy, like for example, the relative entropy derived from Belafkin and Stashevsky? Or some other different
is this the
quantity?
relative entropy that the geometric divergences converge to?
Exactly.
Yeah, so we haven't looked directly at this because the quantity that you want is the conditional von Neumann entropy for these problems. So we were really motivated by the device-independent problem. But we did actually have a paper. So this paper here, which is one of the recent numerical techniques, it actually was it was based on these geometric entropies. So we looked at lower bounds that were based on the matrix geometric mean that we could convert into polynomial optimization problems. So that is, although I think that we defined some new Rénye conditional entropies or Rénye divergences. that were based on these matrix geometric means, and they might converge in the limit as alpha tends to 1 to this BS entropy, but we're not quite sure actually. This was an open problem in this work, so that might be more related, but we've not tried bounding that particular relative entropy directly, purely based on the fact that the relative entropy of interest was the kind of more standard one.
Okay, thank you for the answer. Just one thing, these new geometric range divergences, these new range divergences that you introduced are the slash ones, right?
Sorry?
You're talking about these range divergences that are the slash ones, no?
So in this paper, they were different, actually.
Okay.
So in this paper, they're based really on this geometric mean approach.
Okay.
And we defined some new Renyi divergences in that paper, but in this paper, we defined upper bounds on the relative entropy. In terms of some like weighted sum of these quasi-relative entropies.
Okay, thank you very much. So since I see no more questions, if you have any, just write them in a Slack later, and we'll continue the discussion on Slack and move now to the last talk of the session. Thanks again.
Thank you.